Hi guys, attempt number 2 at chapter 2, lesson 3, polynomial functions and their graphs. This is a huge lesson, 8 objectives, a lot of different things going on here. But for the most part, they all fit together and play off of each other. I'm going to actually present, excuse me, how to use the intermediate value theorem first. That's objective 6, and I believe it's example 8 that goes with that. And then we're going to go back to objective 5, identifying zeros and their multiplicities, with the emphasis there on the multiplicities. And in discussing 5, then we're going to go on to objective 8, graphing polynomial functions, which will be in a separate video because of the amount of time that one requires. With objective 8, we're going to be talking about objectives 2 and 3 and 4 and touching on 5 and 7 as well. So that video is going to be an important one for you to view. Okay, let's get started with intermediate value theorem. All right, objective 6, use the intermediate value theorem. And you're probably thinking, I don't even know what the intermediate value theorem is. Well, this will have big implications for us next year in calculus. But for right now, what we use it for is show that the polynomial function, in this case f of x equals x cubed minus 2x minus 5, has a real zero between 2 and 3. Okay, so a real zero would mean that it has a visible x-intercept between x equals 2 and x equals 3. Okay, doesn't mean it doesn't have other zeros in other places, but the intermediate value theorem takes your perspective and it narrows it to between two specific x values. In this case, x equals 2 and x equals 3. So what we do with the intermediate value theorem is we set up a table. If x is 2, we find the f of x that goes with that. And then again with 3, if x is 3. So using the function given, x equals 2 gives a value of -1, and f of 3 gives a value of 16. Okay, so knowing what the intermediate value theorem says, I can look at that and say, yes or no, the intermediate value theorem guarantees a real zero between 2 and 3. And here in a second, you can too. All right, so what I want to do to create a visual for you is just plot these 2 points. So we're going to plot the points 2, -1, right there, and 3, 16. Okay, you don't have to use Desmos to do this. I just used it to get something here on my screen. You can freehand it. It does not have to be perfect, but your points do have to be plotted in the proper quadrant. If they're in the proper quadrants, then you too can say if the intermediate value theorem says yes or no. Okay, so the intermediate value theorem, one of its disclaimers is that your function must be continuous. We've talked about domain of polynomial functions, of quadratic functions, which is just a more specific group within the polynomial family, and they have an infinite domain. So if you have a function with an infinite domain, that means that you have a function that is continuous from -infinity to +infinity. You can draw that curve without ever lifting up your pencil. Okay, so here comes the real zero thing. If you're coming from x equals 2 and your y value is -1, and you're going to to the point 316, the real zero is an x-intercept. So if you do that, and I'm going to draw it with a straight line, it's really not straight, it's curved, but if you start at this point and end at this point, if your curve is continuous, you had to have an x-intercept somewhere. Okay, that's all the intermediate value theorem says. And you can see that with a nicer graph right here. You can see the actual graph of f of x. It has an x-intercept somewhere between 2 and 3. It may not be an x-intercept that you can find with factoring. You may not be able to do that. You may not be able, well, this is a cubic, so we couldn't use a quadratic formula. or completing the square here. But it would be showing you maybe an irrational 0, one that would have a square root in it. Not imaginary, just not something you could find with factoring. Okay, couple cases where the intermediate value theorem would not prove would be, let's say that you have your point maybe at 2, 8, and then 3, 16. If both of the points are, the y values are positive, intermediate value theorem will not guarantee a 0 between, because you don't have that positive to negative change. If both of them are negative, again, intermediate value theorem won't guarantee that. Both y values are negative. It's only if your y's change from negative to positive, the intermediate value theorem says there must be a value somewhere between, that's where the intermediate comes from, that has a value of 0. Okay, let's talk now. We're going to back it up to objective 5, finding zeros and their multiplicities. So the zeros should not be a funny thing for you, but multiplicity is probably a word that you've not heard unless I just mentioned it off the cuff last year. So example 7, again, finding zeros and their multiplicities. To find the zeros, we're going to factor and set each factor equal to 0 to find those. And they've done you a favor here in example 7 in showing you the function in factored form already. The reason for that is they really want us to focus, and I really want you to focus on the multiplicities of these zeros. Okay, so as you can see, the multiplicity of each zero comes from the degree of each factor. Okay, so we have two x factors. We have the x plus 1 factor and the 2x minus 3 factor. And you can see that the 2x minus 3 factor is squared. That tells us that any 0 that comes from this factor will have a multiplicity of 2 because of the square. The x plus 1 factor is actually to the first. We don't have that number, that superscript out there, but it really is a to the first. So any factor that comes from, yeah, that didn't work. Any factor that comes from x plus 1 will have a multiplicity of 1. Okay, so it's more than just saying this is the multiplicities. The multiplicity has an effect on the behavior of the graph around that x-intercept. And we'll talk about that in a minute. Okay, so setting each factor equal to 0, if x plus 1 equals 0, then we have an x equals negative 1 intercept. And if 2x minus 3 is equal to 0, then we have a 3/2 x-intercept. Again, as I said before, the multiplicity of each factor, the first one has a multiplicity of 1 because of the exponent on the outside of that parenthesis, outside of that factor. And then the 3/2 has a multiplicity of 2. Okay, so you have to have your function factored before you can say what the multiplicities are. That might mean you have to factor it and then say, but factor, find the zeros, and state their multiplicities from the degrees on each factor. Let's go to see what happens with the graph. So the second part of multiplicity is you are able, if you know the multiplicities, to state if the graph actually cuts through or crosses the x-axis at that x-intercept, that's number 1, or 2, if it touches and turns around. So if it touches and turns around, it actually looks like somewhat like a parabola if you would zoom in and focus your attention only on that specific point. Okay, so here's how you know. If the multiplicity is odd, we have that crossing through. I put it on the same level. I underlined those both in red. Okay, and here we have a crosses right there. So I want you to look down here. Which of these two x-intercepts will the graph just cross through? Okay, the odd multiplicity is the x equals negative 1. So pull it over there, x equals negative 1. It cuts right through there. All right, now the other one, 2x minus 3 gave us the 3/2. That had a multiplicity of 2 from this 2 right there. And what we're going to see at 3/2 or 1.5 is that the graph is going to touch and it's going to turn around, staying there in quadrant 1. Okay? That is what multiplicity can tell us. We in the past have had to have a sizable table to get a really good sketch of a graph. But the more we learn about these polynomial functions, we're going to be able to sketch a graph without making a table. If we know, and that's what we're going to do in the next example, but if we know the x-intercepts, the y-intercepts, if we know about multiplicity, symmetry, turning points, those are the 5 steps that we're going to talk about in behavior in the next example, and you're going to have to go to the next video to see that.